Hello everyone, my name is Xiao Wang. I'm with the University of Manchester, and we are responsible for the Work Package 7, the virtual storage plant in the CROSSBOW project. And today I'm glad to share our work with you. Our objective is to provide a framework to coordinate distributed storage technologies, and especially we consider a future scenario in which a large number and different types of storage technologies are available. And the VSP will aggregate those storage units as a single one and provide ancillary services to the transmission network. And the interesting functionalities of VSP are defined in high-level use case 5, including the voltage frequency regulation, congestion management, and the TSO-DSO cooperation and market participation. So our VSP control is based on the distributed communication. And from this figure, we can see the difference between distributed control compared to the typical centralized and decentralized control. So the distributed control has the advantages over these two communication methods, such as it has less communication burden and it can provide more coordinations compared to a decentralized control. And based on this distributed control, we developed the architecture of the VSP. So as we can see here in this figure, each distributed controller of the storage units only communicates to its neighbor. And we mainly consider the storage devices in a distribution network. Those storage units are small in capacity but very large in number, such as those residential battery storage units located in the residence buildings. And we have VSP aggregator to determine the operation of the storage group. And this aggregator has access to the frequency and the power flows in the transmission network. So as I mentioned, the functionalities of the VSP is defined by the VSP aggregator. And the VSP aggregator will determine which services is provided to the transmission network. So in this case, we want to test the performance of VSP in providing frequency regulation to an interconnect power system. And the frequency response is delivered by the translational storage use by reducing the operation costs among multiple VSPs. So, but during the cross-border power transfer, we have to avoid the congestion issues over the tie lines. And as we can see in this figure, this is the 4 TSO networks in Southeast Europe. And we assume there are 5 VSP assets connect to the system at this points marked by the right circles. And each VSP has the architecture as I introduced in the previous slides. The operation principle of all these units in VSP is to maintain a balanced state of charge. So none of the storage unit will use up its energy first and drop out of the response. And then we can see all these storage units will act as a single one, as the VSP in the frequency regulation. So we use this core simulation test bed to validate the performance of VSP. So in this test bed, we used DIGSILENT to simulate the power networks, and the algorithm is implemented in MATLAB, and we use a simple text file to exchange the variables between these two softwares. And in the first case, we test the VSP response in the TSO networks, having 5 VSP assets, and the parameters of this VSP assets can be found in this table. And we can see how many storage units are there in each VSP, and also the cost of the VSP. And for each storage device, the ratings, including the power rating, the energy rating, and the efficiency, is randomly select from this range. And then on the right figures, we can see the simulation results. So at 10 seconds, there is a load increase, and we can see the frequency starts to decline. And then the VSP will respond and deliver the powers stored in the storage. So we can see here. So with this response, we can see improved frequency regulation. And by the end, the frequency is brought back to the nominal value. And also in this case, the constraints on the tie line flow is set to 110 megawatts. And compared to the case without VSP response, we can see the VSP can avoid the congestion issues on the tie lines. And these figures show how the storage units respond in one of the VSP assets. And we can see that the hundreds of the storage device maintain a balanced SOC while delivering the services. And this compares the sum of all storage power compared to the VSP power reference, which is calculated in the VSP aggregator. Furthermore, the performance of VSP is validated in this IEEE 39 bus systems. This systems has 3 areas marked in different colors and 7 cross-border tie lines. And we use the same 5 VSP assets as in the TSO network. So similarly, we assume a step load increase happens at some point, and we will evaluate the response of these 5 VSP assets. So in this figures, we can see the simulation results. Again, the frequency is brought back to the nominal value with VSP response compared to the case without the storage. And also the tie line flows on the cross-border tie lines are reduced to avoid congestion issues. And again, in this right figures, we can see how the SOC is maintained balanced. So individual storage device contribute to the request power according to their energy capacity, and we can see here. So meaning the larger the energy capacity of this storage device, the more power it will deliver during this response, and such that the SOC is maintained balanced. And in this figure, we can compare that the sum of all the storage power checks the power reference determined by the VSP aggregator. So in the last slides, we will show some initial demonstration results. The demonstration will be carried out in the Smart Grid Lab of the University of Zagreb. So in the lab, we will have a series of physical small storage devices. And now we have 3 storage assets connected to the physical network. And these storage devices will be regarded as the storage unit within a VSP. And as mentioned, the VSP aggregator determines the operation of this VSP asset. So in the laboratory setup, we will use the lab SCADA system as the VSP aggregator, which has access to the frequency and the timeline flows in the transmission network. And I want to mention here, the transmission system will be simulated in real time by DIGSILENT. So we have a hardware in the loop testing scheme here. And the initial demonstration results is shown here. So we want to first validate the storage response in this distributed communication network. So we can see here the response of 4 storage controllers. So in the demonstration, we change the power set points in the aggregator, and we can see how the 4 storage controller responds, and they converge to the power determined by the aggregator. And the 2 storage assets is connect to this controller, and this is the real power output of the storage units. And again, it converges to the power determined by the aggregator, but the response is a little slow, and we are still working on this. So in the next step, we will connect the additional storage devices. We have a custom-made battery rack converter, and also we have 5 more water storage units will be delivered to the SGLAB in September. And also the co-simulation test bed. We need to establish the communication between the DIGSILENT and the physical network. And also we will improve the VSP algorithm to bring the SOC balance in the framework.
This is all. If you need more information, you can visit our website at crossbow.eu, on Twitter, on our YouTube channel.